Alright, so this is aynNfire, and I'm going to show you how to make a 2-bit binary counter with a digital display that counts from 0 to 3. So this is the digital display, 1 digit, and basically it's using redstone lamps, and I've connected up all these repeaters and redstone wires so that, well, if you turn on one of them, it turns on one of the segments, and that's going to be useful later on. First, though, I'm going to start with the 2-bit binary counter. So to make that, I'm going to use 2 JK flip-flops. Those are basically just single-bit memory units. I use JK flip-flops just because, well, they're the best. So this is a single JK flip-flop right here. So I'm going to build another one over here just to show you how to make it. Alright. That. Alright. So there, that's how you build a JK flip-flop. I'm not going to go into the details of how the interior part of it works, but I'll explain how the output of a JK flip-flop works. The way it works is if the 2 inputs are the same, then while the pulse is coming into the clock, this one works on rising edge, I believe. So while there's a pulse coming into the clock, the output will just stay the same. You have a pulse coming, so there's a pulse, and it stayed the same. So then if the 2 inputs are different, and you input a pulse, the output takes the value of j. So just input a pulse, the output is 1. So j is 1. And set k to 1 and j to 0. Now I input a pulse, the output is 0. Now, if both the input and the output are 1s, then when you input a pulse, the output is the complement. So it keeps changing. So it's a 0. Oops. Gotta stop doing that. It's a 1. Alright. So that's how that works. And once again, it's a 1, and both inputs are 0, and there's no change with an impulse. Okay. Knowing the truth table, we're going to design this so that the outputs with the constant pulse going through into the clocks, the outputs will be changing through a series of 2-bit numbers, and we're going to make that series 0, 0, 0, 1, 1, 1, and 1, 0. And they're going to each represent, respectively, 0, 1, 2, and 3. So the reason why I'm going to do it 0, 0, 0, 1, 1, 1, and then 1, 0 is because that's a method called the gray code, which makes it so that each two numbers represented in binary are only 1 bit apart in distance. The next thing is to use the truth table of the JK flip-flop and look at the present state values of the output and the next state values of the output to determine what J and K are for each of the flip-flops. So this one's going to be, so this is A, this is B. So these are the outputs that we want, and we want A and B to be 0, 0, 0, 1, 1, 1, 1, 0. So to have that, we put the present state column, then we create another column called the next state column, where we put A and B again, but we put the state that A and B will be once the first clock cycle comes in. So when it's 0, 0, when the clock cycle comes in, A and B become 0, 1. When it's 0, 1, A and B become 1, 1. When it's 1, 1, A and B become 1, 0. And when it's 1, 0, A and B become 0, 0. By looking at the present state and the next state, we can determine that J and K will take the following values. So A changing from 0 to 0, J could be only 0, but K can take either 1 or 0 as value. So we just mark it as X, because we can pick whichever one we want. And then we do the same for the rest of them, using the truth table to figure this out. So here are the rest. So now that we know that, we can use these results to figure out the inputs for JA and KA and JB and KB. By comparing the columns of JA, KA, JB, and KB to the present state values of A and B, we can note the following. JA actually equals the output B, and KA actually equals the output B inverted. So we can take the B output and take it all the way over to the two A inputs, and we can take the A output and take it all the way to the two B inputs, because it's also going to be JB equals A inverse and KB equals A. So let's just do that. Now we have the output B inverted going into KA, and the output B directly going into JA. Then we have the output A inverted going into JB and directly going into KB. Now we need to set up the clock. Or the pulse generator, I should say. So I'm going to use the following pulse generator. Now, I figured out the delay I needed by trial and error, but I'm sure it doesn't have to be exactly the delay that I am putting on this. This is just so that in between each two pulses, there's enough time to see the actual output. Oh, you don't actually need a wire there. So now, if I flick this, this shuts off, but just before this shuts off, it passes the power through this block, which starts up the pulse. So that's our pulse generator. Now that we're going to hook up to the two clock inputs. So let's make sure that it reaches 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's not going to reach, so we'll put another. So now we've got the two clocks connected to our pulse generator. So we turn on the pulse generator. Now that we've got the pulse going, we should see the outputs changing. So 0, 0, 0, 1, 1, 1, 1, 0. So just a note, 0, 0, so that's A, 0, 1, 1, 1, and 1, 0. So we've got the correct outputs coming out of there, and there's actually a very nice delay in between, so there's actually long enough time to note what the outputs are. Now, we use the following table to determine the outputs needed to create the inputs for the digital display. So you have the A and B column, so 0, 0, 0, 1, 1, 1, and 1, 0. Then we have the following column for the digital display. So we have D0, D1, D2, D3, D4, D5, and D6. These columns represent these segments. So, hold Hold on. Just reset the light there. Okay. Now we look at each one of our inputs, or our number values that are in our series. So 0, 1, 2, and 3. And we figure out how we want the segments to light up to represent those numbers. So for 0, we want D0, D1, D2, D3, D4, and D5 to be on when it's supposed to represent a 0. Meaning the first row is all 1s except for D6. Then we want, for 1, only D1 and D2 to be lit up when it's a 1 as the output. And we do the same kind of deduction for 2 and 3. By initially looking at the table that we just created, we can tell that D0 and D3 are equal. Those two columns are the same. So we'll only need to have one gate for both of those inputs. So that's D0 and D3, which conveniently are right next to each other. Then we can see that D2 is clearly always on. So what I'm going to do here is first D0 and D3 require the same input, so I'm going to connect them so that I know that. D2 is always on, so I'm just going to turn it on. And D6 is actually just equal to the input, or the output A. So that one will just have a direct link to A. To determine the gate needed for D0, we can use the following method. We use the Carnot table. I think that's how it's pronounced, or Carnot. I think it's Carnot. Anyways, we use the tables that are basically the following. So it's a square, and we have both inputs, A and B, and we have the 0 box, the 1 box, and the 0 box and the 1 box for the both A and B. So now we have these 4 boxes, so each one represents one of the pairs of inputs. So it's 0, 0, 0, 1, 1, 0, 1, 1. And we put the values of D0 into those boxes. 1, 0, 1, and 1. Then we can use this box to determine outputs, or sorry, the gates that are required to create D0. So we take this box of 1 and 1, and we can see that regardless of the value of A, one of the possibilities of the values of D0 is B inverted, which is represented by this 0. Then we take this box over here. Because we've already used both these ones, we can't use them again. So we can see that this one shows us that the other possibility of the input of D0 is A and B. So from that we have the input of D0 is either B inverted or A and B. Using basic logic reduction, or gate reduction, sorry. Using basic gate reduction, we can tell that A and B or B bar is the same as A or B bar. So the input for D0 is actually going to be A or B bar. Use similar method to figure out the rest of the inputs. So using this method, I determined that D1 equals A bar or B bar, D4 equals A or B inverted, the entire thing, D5 equals A exclusive or B, the entire thing inverted. So now we have the entire list from our initial examination, which gave us D0, or which gave us D2 and D6, and told us that D0 and D3 are the same. And we have all of the other gates needed from the examination of the input relation to the digital display output relation. I just said relation twice, which I shouldn't have done. Okay. Now I'm going to build. So here's our inverted OR gate for the input D4, or the output D4, I should say. Our exclusive OR gate for the output D5. Our OR gate for the outputs D0 and D3. Our direct link for D6. Our OR gate for D1, D1, and our 1 for D2. Now, I have to hook these up to... So now, all of the gates are connected. We have our inverted OR gate, we have our inverted XOR gate, we have our OR gates, we have our direct input, and we have our 1 input. Now, we can tell by the 0 on A and the 1 on B that our output should be a 1, based on the design that we made. And there it is. Finally, oh, don't want to fall there. Finally, we can switch on the pulse generator and watch the display change values. 0, 1, 2, 3. As you can see, there are some delays in the segments switching on and off, but that's fine because we leave enough time so that you can tell which number we're at. And that's a 2-bit counter that counts from 0 to 3 with a digital display. If you have any questions or comments, leave them in the comment section below. Yeah, that's it. Thanks for watching.